Hi, I'm Ilya. I haven't posted videos for a while because I've been participating in LeHome challenge, the competition in which I needed to train bimanual robot like this to fold different types of garments, something like this. This competition consisted of two parts. The first part was in simulation, and I used a lot of reinforcement learning, combining both existing techniques and some new ideas that I come up with myself, and eventually I won this first part. The second part was offline on site of the ICRA, and I used a lot of human-in-the-loop interventions like Dagger-style data collection to improve my policy and to do this sim-to-real transfer. And eventually, I get the second place in this second phase of the competition. So I already open sourced my solution, so you can find everything online. But in this video, I want to go much deeper and I want to explain why I made different choices, how I thought about this problem, what are the alternatives, and why I chosen the ones that I've chosen. And while preparing for it, I realized that it's like a lot of information. It will take hours to actually explain all these things. This is why I decided to split this video into three parts. And today will be the first part. In this part, I will talk about reinforcement learning, about overall reinforcement learning loop that I use to train my policy. I will explain why many of the approaches that are kind of common in reinforcement learning are not very suitable for VLA trainings. And I will show which approaches actually work and what I've chosen. And finally, I'll talk about data collection. I will explain how I optimized the whole process, how I augmented all the rollouts to collect more diverse data, and what strategies I use to do it. And then, of course, I'll talk how all these things work together, how I organize the reinforcement learning loop that works completely asynchronously, where you can scale any part of it independently, and many other details. And then in the follow-up videos, I will talk about reward engineering, about inference optimization, and then we will discuss the second round where I did a lot of sim-to-real and human-in-the-loop interventions. I will show how to move your policy from working in simulation to real robot and discuss all the problems that I faced and all the nice tricks that I learned. And let's begin. A good way to learn about competition is simply to open its website and quickly go through all the materials that are presented here. They have this quick overview, then more detailed explanation of two phases, and we will talk about the first one very soon. Then, of course, competition ended, so you can see the leaderboard already here. And then some extra information, prizes, and so on that you can find here. While we are in the bottom of this page, I want to say thank you for the Lightwheel, who was a sponsor of this competition, then organizer committee, and of course all the organizers to help to make it happen. I really enjoyed this competition, so thank you very much for organizing it and making it work. And now let's quickly go through the description of the first phase. The first phase is the simulation challenge, and in this phase we are given different garments of 4 different types. It's long sleeve tops, short sleeve tops, long pants, and shorts. And the idea is that we need to train this robot to fold these different garment types. We'll talk about data a little bit later. The one very important thing is that we look only at the full success rate. So we need this kind of garment to be completely folded to consider it as a success. And this success is defined by different key points. So for example, you could already see that there are 2 key points on the sleeves, and they should be connected to each other. And then there are other key points that are used to define whether we folded this short in half. And you can see that then we automatically check distances between different key points. Some of them should be very close. The distance should be below the threshold. Some of these points should be far away. So it means that we didn't just put everything together in one point, but the garment is spread. I would say that it works pretty well, all these key points logic. Maybe there are other ways to actually fold the garments in the real life, but particularly for this competition, there was some standard approach, standard folding strategy that we should have followed. So yeah, you can see how it works for the long and short sleeve shorts, and then now pants, and finally you will see how to do it for shorts. So this is the example of the failure because these two key points are a little bit too far from each other. So yeah, this is not completed task. Finally, the shorts are the simplest one, just fold them in one movement. And in this case, this is the example of the success. This is it that you need to know about the rules themselves, how we can see whether the episode is successful or not. For more information, you can look at the actual rollouts. So the data provided by organizers is shared on Hugging Face. For example, this is top view of part of the data shared there. For some reason, it's flipped 180 degrees. So when I trained my models, I kind of flipped it back. But yeah, this is just the decision to put the camera this way. Yeah, so basically we have a lot of rollouts like this that we can use for the initial behavior cloning. Sometimes they're better quality. Sometimes you see there is one episode sleeve was a little bit outside, so it probably was on the very, very, very edge of the success. And yeah, so we basically have this data set for different type of garments that we can start our training from. And finally, there is a repository with all the code needed to start competing in this challenge. So this code provides you the environment for the simulation where you can run your policies to evaluate them or to collect more data. Also, they provide some starting model training kind of logic. You can use models that already exist in the robot and just follow the instructions to train your first version of this model. And of course, they provide all other instructions and extra details, as well as information how to submit your solution for the actual competition. If you want to know more about the competition, the rules, the environment, and so on, I would just recommend you to simply go here and try to run it yourself or just read through it to understand more details. At this point, you may ask, why is this competition hard? Yeah, so this task of close folding is not something unsolvable. Yeah, if you look at the past, maybe 3-4 years, then it was very, very hard task. But then recently, when we started to use all of these end-to-end policies, different VLAs and so on, different labs started to actually show demo where they managed to solve this problem. So why is it hard here? So first of all, this problem kind of solvable now, but it's not trivial. Yeah, so I still see demo of some robotics companies that are kind of trying to do it and it doesn't work well. So it's it works well sometimes. Indeed, some people kind of solved it, but it's not like everybody can solve it 100% of the time. The second one, of course, this is competition. Yeah, so it's not I need to make demo that works once. I need to train the policy that actually consistently can solve this problem again and again and again and do it better than other competitors. Third, we need to use these robots, and these are pretty cheap robots. They have some problems like backlash, or sometimes they cannot properly kind of grab the fabric because of this gripper and so on. And we cannot modify the hardware anyhow, because again, I've seen some demos where people fold t-shirts with this robot and then they put it slightly differently and so on, and then find the best configuration, how to set it up to make it work. Again, it wasn't an option for us in this competition. So we needed to just put it in some particular setup with exact positions of all the robots and so on. And of course, you cannot change the gripper or any other things because you need to run it on the organizer's setup and that. Then, and this is the next problem that I just mentioned, in the finals, we needed to run it on the setup on the robot that we've never touched and never seen. So I have this robot here, but again, because they're very, very cheap, every time you assemble it, every time you calibrate it, every time you use slightly different camera or camera mount, they work slightly differently. And we needed to train the policy that generalizes good enough to work on the different robot from the same family, but with slightly different camera, with different colors. For example, the final robot was orange and I have red robots here, and so on. So there are a lot of challenges to train pretty robust policy. I just wanted to remind you that I already open sourced my whole solution for both phases, and you can find everything online. So first of all, I have this blog post. It has a lot of visuals and a high-level explanation of my solution with some details of the most important things that I implemented. So if you want to kind of know the rest of the story before I released my videos, then you can definitely open it and check like more examples and quickly at least read through it. If you want to know more details, I also published the whole tech report on archive with much more details, with much more like explanation of what exactly was done. So again, for like more deep dives, you can always refer to this paper. And finally, I released all the code, so you can reproduce everything that I'm talking about here. So everything that I implemented is available on GitHub. So feel free to try to train your own model or run some evaluations with checkpoints that I also share. And yeah, if you have any questions related to it, please don't hesitate to ask me. When I first seen the announcement of this competition, I was looking for a playground where I can test some ideas that I had in my head about reinforcement learning for VLAs. And this problem sounds very nice because on the one hand, it's not trivial. It's a kind of relatively hard problem. But at the same time, the episodes are pretty short. So in terms of kind of compute, for example, GPUs, I don't need the whole cluster to train these models. I don't need the whole cluster to collect the data. We are talking about, I don't know, 10, 20 seconds episode that is kind of, again, not super short, but not super long to waste a lot of resources on this training. So again, it felt like a very nice playground for reinforcement learning. So I originally joined the competition for the first round mostly, but then of course there was the second round with a lot of sim to real and kind of some Dagger data collection and other interesting things that I also wanted to experiment with someday. And it was just nice that everything was combined, and it was like one big experience to do all the things. So yeah, this is some rationale about competition, about why I think it's interesting, what was my motivation for this. And now let's start talking about the solution, and let's go deeper into the reinforcement learning part and discuss how it works and how I applied it in this case. First of all, the common reinforcement learning loop is to train your policy on some data that you usually have in the beginning, then collect more rollouts using this policy, then train value or Q model using this collected rollouts, and then use the prediction of this model and the collected data set to train policy again and improve it. And then you keep repeating it again and again and again, and eventually your policy becoming better. So this is more or less how like most of the reinforcement learning policies work. I decided to kind of simplify this process. So the first thing that I did, I combined policy and value function together. We'll talk about it a little bit later, but my value predictions are coming from the same model that action predictions, that the policy itself. So now I have only two parts, two kind of streams of work. One is the policy and value training in one go, and another one is rollout collection. And these are two different types of tasks to do. In many cases, again, when you look at the mainstream approaches in reinforcement learning, they are run sequentially. So you train policy, collect rollouts, train policy, collect rollouts, and so on. And it's not very efficient, especially given that you need to use different type of GPUs, different machines for these two tasks. And maybe if you do it like in one machine, it's not optimal. In general, I wanted to make it as asynchronous and as distributed as possible. This is why I put these repositories between them. So I use Hugging Face repositories for models and data. And I put them in between these two processes and made them completely isolated from each other. So policy and value training process never talks to the rollout collection process and vice versa. They simply interact from the Hugging Face hub. Let's add a little bit more details and talk about it one by one. So first of all, we have a training machine. In my case, I use the machine with one H200, but if you want to scale it, you can just use like more powerful machine with more powerful GPU. So maybe, I don't know, 8 GPUs in one machine, and it will work out of the box. So this machine, at any point in time, downloads any new data sets in the data repository, then compute some statistics and compute advantages based on everything in this data set without actually using any predictions of any model, and then run the training loop. So using this new data set, combine it with the old data sets, and run some steps of training, and then usually like every half an hour to hour, it generates a new checkpoint and uploads it back to the Hugging Face repository, but this time different repository with the model. And then there is the second part is rollout machine or machines. You can use any number of machines you want for this, because again, everything is completely independent and asynchronous. I mostly use my RTX Pro 6000 machine, and also sometimes a little bit different, and sometimes I kind of used more machines when I wanted to collect more rollouts faster. But each of this machine completely independently download the latest checkpoint from the model repository, run evaluations, so collect new rollouts, make predictions of value and completion, that something that we'll discuss later in this video, and then uploads all these new rollouts with some extra things like identified hard states and so on to the data repository. And then this cycle simply begins. So the main idea here is that these workers, they don't wait for each other. Whenever you start new rollout collection, you just use the latest model checkpoint available. You don't care what's happening on the training side. Whenever you do training, you just use all the data available at this point. You don't care what's happening on the rollout side, or whether even rollout exists. Maybe you can kind of stop all the rollouts and train model more, or you can stop all the training and collect more rollouts if you think that one is going behind another. This is the main point. So like my approach, my pipeline is completely asynchronous. Nothing is waits for each other. Everything works with the latest data or models available. And it's very easy to scale any part of this pipeline. Technically, there is also the third part. It's manual teleoperation and Dagger data collection. So this also can run completely independently. It doesn't need any model, but it can take the recent hard cases stored in the data repo, and then you can collect new rollouts manually, controlling the robot and simulation using the leader arms. And I initially thought it will have a big impact on the final solution. In practice, even so I collected some rollouts, it wasn't so important, and I will talk about it a bit later. So it was very, very important to collect this Dagger rollouts in the real second round. And I will talk a lot about it in the second video, but it wasn't so important for simulation. And just for the sake of time, I decided to move this discussion about this simulation Dagger data collection to the second video as well, because it wasn't really a big part of this story here. So you can keep in the back of your mind that I did collect some rollouts manually, but it wasn't like a big deal here, so you can kind of forget about it till the end of this video. But now let's talk about the actual reinforcement learning approach that I used, because not every approach can be actually applied in the pipeline that I've just discussed. Before we begin, I just wanted to quickly go through the glossary of reinforcement learning to make sure that we speak the same language, and then show some mini example. So first of all, policy is basically our model that decides what actions to take next. The reward is our feedback that we instantly get at any step. And then if you accumulate this reward over the whole trajectory, starting from the current point, we'll get return. And return, this is what we actually optimize. This is what we want to maximize in the end. Then the value function is the expected return that we will receive starting from the current state. And the Q value is expected return that we will receive starting from the current state if we make one particular next action that already pre-selected. And finally, advantage is difference of these two values. I will use a lot of these terms during the explanation, so I wanted to list them here. But now let's look at the actual example and kind of repeat these definitions again to make sure that everybody understands them. So in the beginning, our environment starts from some state, And in this state, we can take different actions. And our policy is something that predicts the distribution of these actions and then somehow samples from this distribution and select the particular action. Then when we move, for example, from state 0 to state 1, we get some reward R0. When we move to state 2, we receive some reward R1 and so on. And then this reward is getting accumulated, and if we sum up discounted rewards, we will get our return. And this is our final kind of target that we are trying to maximize in the reinforcement learning. Then if we just think about all possible trajectories that can go from some state, average them, or like compute the expected value of the return from them, we will get our value function. If we do the same with one pre-selected action first, we will get Q function. And finally, if you look at the difference between these two values, Q minus V, we'll get advantage. Advantage shows how much the current action is better than the average action in terms of expected return that we will get from the current state. I hope now everybody on the same page, and we can go deeper into discussion about the algorithms. First of all, before going to reinforcement learning, let's remind ourselves what is behavioral cloning. So behavioral cloning is not reinforcement learning approach. It's more like supervised machine learning approach where you have some training data and then you train the model to kind of replicate this data. In our case, we have like some data of like maybe teleoperated robot or maybe collected by other policies or maybe somehow else. And we train the policy to replicate the actions that were taken by whatever was used to collect the initial training data. So you can say that you have like initial training data set D consisting of states and actions taken in these states. And then in other words, you can say that you have this implied policy mu. So even if data was collected by human or by like some mix of policies and so on, you can always say that there is some implied policy that will collect equivalent data kind of. And then basically your policy that you are training is trying to replicate these implied policies, trying to replicate the behavior of whatever was used to collect the original data. Depending on the model that you use, you will train it a little bit different. So for example, if you train discrete model to predict discrete actions, you will probably maximize log probabilities of every action taken given current state. If you train some regression, then you will try to kind of predict some average action taken in similar states, but this is not a popular way to do in robotics, so we will talk about the second one. So when you think about all the formulas in the future, it's much simpler actually to think about them as if we are solving discrete problem, because I think a lot of these original approaches were derived for discrete problems, but they work kind of the same for the continuous actions as well. But again, when you're like thinking about overall concepts, this kind of discrete action space sounds much easier. So I like recommend to think in discrete terms when you think about formulas, but then kind of go back to the continuous when you really need to train the model. But the flow matching that we use and many VLAs or many other models in robotics use nowadays, it's like a common choice of the action head, of the action expert, works differently. So it's not discrete. It predicts continuous actions, but it's not actually predicts actions. So flow matching predicts some velocity field, basically some process that can transform any distribution into any other distribution. In practice, we mostly start from the normal distribution and transform this normal distribution into the target distribution. We have, again, some normal distribution. We sample any point in this normal distribution. And then this prediction of velocity is basically some bunch of vectors that guide how this point should move into space to land somewhere in the target distribution. And then if you like apply the same logic to all the possible sampled points from the initial normal distribution, we will eventually generate our target distribution. And this is how this model is trained. So when it's trained, we just minimize MSE loss in this velocity space. During rollout, we sample any random vector from the normal distribution and apply these velocities, this process, to transform it into the final prediction in the target distribution. This is nice during rollout because during rollout we just need one action chunk, one kind of point. to use, to execute, but it's not very well for reinforcement learning, and we will see it very soon. And the problem is that we never explicitly model the target distribution. What we learn to do with flow matching is to sample from the target distribution. But we cannot, for example, predict the probability density for some action in the target distribution. This is not how it works. And again, it will define a lot of our choices on the following slides. And I think this kind of applying reinforcement learning for flow matching is not completely solved problem. There are like a lot of new ideas there. There are a lot of difficulties because of this approach. So it's kind of very interesting area right now, because on the one hand, everybody using it for behavior cloning. On the other hand, like reinforcement learning seems very promising, but it's very hard to use reinforcement learning for flow matching. So overall, it's like very, very interesting field. Okay, so we talked about behavioral cloning. Behavioral cloning, again, is like something that tries to replicate the expert behavior, expert approach, but it's not what we want in the end. Yeah, so in the end, we want our policy to act better than expert. So we want our policy to be like, I don't know, faster, higher success rate, maybe improve some other metrics. And this is why we need to use reinforcement learning here. And the reinforcement learning idea is instead of trying to mimic the expert, let's try to directly optimize what we want. Yeah, so if we can engineer some reward and return that actually correlates with what we want to get in the very end, let's just train the model to directly maximize this value as much as possible. In most of the reinforcement learning approaches, this formula here that is return, that missing some of discounting factors to make it simpler. So this return is what we're trying to maximize. And then there are different approaches how to do it. So approach number one is on-policy methods. On-policy means that you use very fresh current policy data. So you have like your current policy, you collect some rollouts, then using some formulas that you can see on this slide, you can actually directly compute the gradient of the policy towards the direction of improvement of the return. You take like the rollouts of your policy, and again, mathematically, you can show what is the direction of the policy change that will lead to higher return in that. Couple things here. So first of all, you can see that first formula doesn't have any return anymore. It switched from optimizing expected return to optimizing expected advantage at each step. I will not prove this formula here, but it's kind of some fundamental observation. So instead of maximizing return, you can kind of maximize the relative goodness of every action at every step, and this is an equivalent problem that eventually leads to the higher reward. And yeah, in most of the cases, we simply switch from return optimization to advantage optimization. This is how it works. And then the second formula represents the exact formula of the policy gradient for the maximization of return. First of all, I mentioned that you need very fresh policy data. And technically, this data should be extremely fresh. So it means that when you collected some rollouts, and then you run optimization, and then you make like one gradient step, your policy already changed. Yes, so like after the first gradient step, you're already dealing with another policy. And technically, you cannot use the on-policy methods anymore. As soon as you made the first step, it's not on policy anymore. So you literally need to collect rollouts, make one step, and then collect rollouts again. It's like extremely inefficient in terms of data collection. The second thing, if you look at these policies, you see this like probability or probability density of selecting some particular action given the state, or even like log probabilities here. And as I told you before, flow matching cannot predict these probabilities. So flow matching just samples from the distribution. Flow matching cannot tell you what the probability to sample this action, what the log probability, what's the, I don't know, probability density for this action. And this is kind of the fundamental part of this formula. So you literally cannot apply this formula to flow matching directly. Let's look at some other approaches. This on-policy recency data requirement is very strict. So in practice, we want to relax it. We want to be able to use like little bit like older data and at least collect the fresh data and then do a few steps to update the policy. This is where this kind of less on policy, let's call it, methods becoming useful. So technically they still attributed to on policy, but they have some off policy features. The most popular idea how to improve this data efficiency is to add this extra correction with pi theta alt that basically represents the probability that this action would be selected by our old policy that was used for the data collection. And it's very, very widely used approach. And one of the most popular methods in this family is PPO. It's used basically everywhere. Nowadays, it uses the same approach, but adds some extra tricks, extra clipping, and it allows to train our policy for more steps from the data that is collected once. They still require to collect data with your current policy, then make some number of optimization steps, and then completely discard all the old samples and then collect new data and keep training on this new data again and again. It's much more data efficient when we do it in this way, in this PPO way, but it still requires a lot of data. Another problem that we discussed before and still exists here is that we need to predict these probabilities. So again, this pi represents either probability or probability density of different policies, either the one that was used to collect the data or the one that is optimized right now. And again, we don't know these probabilities. We don't know these predictions when we use flow matching. So you cannot really apply flow matching directly using these formulas. It's a very, very fast developing area, and there are approaches that are trying to apply PPO to flow matching or diffusion or some similar models. But the problem with all of them, or at least the ones that I'm aware of, is that they're not really directly applying PPO to the original problem. Usually what they do, they make the problem a little bit more complex. They add some extra steps or they make some approximations, and then they apply the PPO to this approximated problem or this like changed problem. And again, it doesn't directly do the same thing that PPO does. So I would say that this PPO for flow matching is not 100% solved, even so there is some progress and there are some approaches that people are trying to use. But I didn't use them, so I decided to go for a different approach. And I'm using this advantage weighted regression policy. And this is a policy from off policy method. It doesn't require to use very, very recent data from the very recent policy. It can accumulate data set, it can collect data from different policies. And I would say that this approach even works offline. So even if you cannot collect any new data at all, but you already have some data set, you can apply this method on top of this data set and train the policy that is better than behavior cloning. So this is nice. This is what we want because our data is kind of expensive, and it's often the case in robotics. You don't want to discard old rollouts half an hour after you collected them because they're not on policy anymore. So you want some policy that can actually deal with old data, especially data collected by other policies, by people, by human in the loop using some Dagger things and so on. So this approach fits much, much better to our needs. And let's look at it. So first of all, look at the formula on the left. You may see that we don't have pi old anymore, and pi old is replaced with mu everywhere, but it's basically the same formula. So just before, we assumed that we have some very recent policy that we use to collect the data. Here we don't have this policy explicitly, but we again can assume that we have some data set, and this data set has some implicit policy mu that represents some combined policy that was used to collect this data set. But again, this formula is very, very similar to what we've just seen. And the main addition here is this KL divergence that shows how our new policy pi differs from this policy mu. And if we add this constraint that says that this KL divergence should be below some epsilon, then you can derive the closed form solution for this problem. I'm not deriving it here, but it's actually a nice exercise, so you can just try to do it. If you do it by hands, you'll probably understand better how it works and why. But I'm just showing the solution here. And this solution is very nice for us because it doesn't require to predict any probabilities anymore. What it says basically is that the optimal policy that solves this problem above is simply reweighted mu. So if you have this mu distribution, and reweight it with weights proportional to the exponent of the advantage divided by some constant. Then you will get kind of new distribution, and our new policy basically should sample from the distribution. And as we remember, our flow matching approach is good at sampling from any distribution, and it doesn't really care from what distribution to sample. And this is exactly what we need to do. So we just need to train the model that samples from a new distribution. Instead of sampling from mu, like behavioral cloning doing, we need to sample from this reweighted mu, where the high advantage actions have higher weights. So you can see that this approach doesn't have these two problems that we just discussed on policy methods. So it doesn't require to predict directly any probabilities. And it allows us to use all data, even if it's collected without any policy, but with humans or somehow else. This is very, very good. And this is exactly what we need in this case. Specifically, for this closed form solution, if you use flow matching, it's extremely trivial to make flow matching to sample from this new weighted distribution instead of original distribution. To do it, we simply need to add one weight. So we simply need to add this exponent in our loss function that we are optimizing, and it's done. Literally, it's like the same process as behavioral cloning, no other changes, just we add one extra weight to our loss, and kind of magically, the policy that we train starting to be better than the original policy that is implied for our collected data set. That is kind of very cool, and it directly allows us to use flow matching for this reinforcement learning problem. In practice, I also clip advantage, and I use beta equals 1, so my formula looks like this. And even bigger change that I implemented in practice, instead of using these weights during the training time, instead of using the weights in the loss function itself, I keep the loss function exactly the same as in normal behavioral cloning without any changes at all. But I apply these weights during sampling. Whenever my data loader samples from some data set, it samples proportional to this exponent of clipped advantage rather than sampling uniformly. So I believe it's even more efficient, because if you have some very, very bad actions in this top approach, we will sample this data, load them, and then train the model with extremely low weight for this particular sample. In the second approach, we just never even, very rarely even sample such bad actions. And we have more variants of better actions in every batch that we use. So I think it works a little bit better. Again, I didn't ablate it properly, but I believe that kind of this weighting through sampling is just more efficient than weighting through weighting in the actual loss. This is literally the only change that I needed to do. I just needed to add extra sampling probabilities logic to the data loader and then run the same pipeline that I use for behavioral cloning. Now let's look at the very simple example, how it works in practice, and if you simplify everything as much as possible. Let's say that we have a distribution of data that has both good and bad actions. Bad actions are red here, the good actions are green. They all have some advantage. Good actions mostly have positive advantage, bad actions mostly have negative advantage. There is some spillover just because advantage estimation is always noisy. We never perfectly measure it. If you train our behavioral cloning policy, it will kind of resemble this distribution. But now we add some weighting, and as soon as we apply this weighting, the kind of target distribution is getting rebalanced, and all the actions with positive advantage or high advantage get much higher weight, and eventually our distribution moves towards the right side and moves towards the good actions. Again, this is very, very simplified example. In practice, of course, the process is much more complicated, and of course, it's not one-dimensional. But high-level idea is like this: learn good actions a bit more often, bad actions a bit less often. Okay, but this AWR is not the only logic that I used. I combined it with another policy that is called the RECAP. And this policy is proposed by Physical Intelligence in the Pi 06 star paper. I would recommend you to read this paper to get the actual logic, derivation, and formulas. But what I found is that their kind of derivation is a little bit overcomplicated, because they derive it with very, very general assumptions. And then they kind of apply some simplified assumptions in the end and make everything much, much simpler. on my explanation, I want to start with this already kind of simplified things and just explain intuition behind the recap. But again, you can find the whole derivation later in the original paper. Let's look at our mu. Yes, this implied policy of the training data. You can use this like total probability formula to split it into two parts. The one is kind of distribution of actions with high advantage, multiplied by probability by like a share of good actions with high advantage, plus the distribution of actions with bad advantage, multiplied by corresponding probability. It's like very, very similar to what I just shown you like in the previous kind of example with this red and green actions with different advantage values. You can see that kind of there is this conditional distribution of only good actions, and in practice, this is what we want to predict. Yeah, so we want our policy to predict only good actions. Yeah, we don't want our policy to predict bad actions at all. And why don't we just train this model, train our policy to predict them? Yeah. So actually, there are like I think approaches that try to do exactly this, try to predict exactly the like train only on like good actions, but I think they're losing eventually because the bad actions still have some important information. They have information about overall distribution and so on, and they also kind of show the policy that these are the possible states. And actually, policy can sometimes learn what would be the good actions for these states, even if it didn't see it in the training data. So it's not necessarily good to completely throw away all the bad actions. And this is what RECAP is doing. So RECAP is training the same policy, same model in two modes. Mode number one, it's kind of unconditional pass when we don't send any extra inputs. And in this case, our policy that we train simply predicts the implied data policy. That's exactly what we have in the behavioral cloning approach. And then we also train the conditional pass. In this case, we provide one extra input to the policy and literally ask policy to predict only good actions, only like this orange part of the formula above. And this conditional good action pass is like it's sharing the same weights. It's like using exactly the same model as the first pass, but it gets one extra input that literally tells policy to predict better actions, predict only good actions. And surprisingly, policy does it. So surprisingly, policy starts to predict the kind of better actions when you simply ask it to predict better actions. And then during the actual rollout, we don't need unconditional pass. We use only conditional pass, and we just say predict good actions, and the policy predicts good actions. In practice, we can go even further, and we can apply classifier-free guidance to make good actions even better. And I will talk about it in the inference optimization section. Now let's look at the same example, but applying recap logic instead. So when we kind of move this epsilon to the right and increase it, we force model to predict like more and more high advantage action distribution rather than any other action distribution. And again, we shift the weight of the good actions in final predictions higher and higher. Now let's compare these two approaches. On the left is the formula that you already seen. On the right is a formula that you can get if you try to actually like derive what eventually RECAP is doing. And you can find it again in the original paper. And the idea is that they actually doing very similar things. So on the left, we take the original implied policy and reweight it with advantage, exponent of advantage. And on the right, we do very similar reweighting, but we reweight with the probability that the advantage is higher than some threshold. In practice, this probability function can be like a step function, but because of the noisiness of all these advantages and so on, it's maybe like more smooth. But again, the idea is that we simply reweight the target distribution with slightly different logic, and in both cases, we get better results than the original policy. And in my final solution, I simply combine these two approaches together. I just use them simultaneously. So on the one hand, my kind of baseline prediction of the model getting better because of advantage weighting. And on the other hand, I still have this like extra conditioned pass that predicts even better actions and also unblocks this classifier-free guidance that I will discuss later to predict like very, very good actions. And I think this combination actually have this additional benefits, and it's a very good idea to combine them together. One extra thing that I like in this approach is that these approaches are not punishing bad actions. They just redistributing the weights, and it's nice. Because imagine that you use kind of any other approach, and many of these approaches, they increase the probability of good actions. Whenever they see good actions, that is fine. But when they see bad actions, they kind of reduce the probability of bad actions. And the problem is that we are dealing with a very high dimensional space. Imagine in our problem, we have like 2 arms, total 12 degrees of freedom. We predict 30 steps forward. So we have like 360 numbers that we predict at every model kind of forward pass. It means that our kind of predictions sit inside this 360 dimensional space. But the actual manifold that contains the reasonable actions, the reasonable action sequences, is much, much smaller. It's just very, very tiny subset in this high dimensional space. The problem is that when we kind of discourage model from predicting bad actions, there is no guarantee that we will stay in the same manifold. Yeah, so we'll kind of reduce the probability to predict this bad action in the future, but this kind of probability will be spread across all other actions. In a good scenario, yes, it will just move to the good actions. But again, in many cases, it's not guaranteed. So these actions, this probability can just flow to completely nonsensical actions. That is not nice. And in case of these approaches like recap or advantage weighting regression, we are not kind of discouraging bad actions. We simply move probability towards good action. Even when we have bad action, we train to kind of replicate this bad action. It just happens not so often. So I think it kind of helps in sense that we are not going away, we are not going from the manifold. But on the other hand, it's actually a problem because these approaches don't have any natural discovery, don't have any natural exploration. So our policy will never try anything new ever. And yeah, this is some limitations that I also face. Yeah, because I've seen literally zero exploration in my approach. So model never learned new behavior. It was just improving to do the stuff that was already seen in the training data, and managed to do it better and better and better over time, but it never learned any new tricks. Okay, so there were a bunch of formulas. I definitely didn't go very, very deep in all the reinforcement learning details. It will take many hours to explain everything in reinforcement learning. I will actually refer you to the Stanford course from Chelsea Finn in the description. I think it's one of the best courses in reinforcement learning that you can find online right now. So if you want to know much more details about it and how all the things work, I encourage you to watch it. It's very, very cool. I really liked it. So let me just maybe give some intuitive summary of what we just discussed. So there are a lot of approaches in reinforcement learning. Reinforcement learning generally tries to improve on top of the collected data and train the policy that directly maximizes the reward that we can get in the future. And many approaches are not applicable when we use flow matching as our final action prediction head. And this is exactly what we are doing here. So I propose to use approaches that are completely usable with flow matching, because instead of trying to predict some policy gradient, they just try to kind of reweight the target distribution and then simply use flow matching to learn this distribution. And I argue that combination of these approaches is even better, and we can use them together to achieve better results. And this is basically the main logic of my solution. And now let's discuss the architecture of the policy that I used. My policy is based on the PyO5. You can see that it consists of this main VLM part that is trained on top of PolyGemma that consists of Gemma and siglib. And also it has this flow matching action expert. It's taken directly from PyO5. But I didn't start from the raw PyO5. I used the solution of behavior challenge that my team won last year. We also used PyO5 as a baseline back then, but we introduced a lot of changes into the architecture. I basically used all of them in this competition as well with some small changes. So if you want to know more, I would recommend to just refer to my video about behavior challenge. And here I will talk more about the extra changes that I introduced for this LeHome competition. We already discussed that our policy should be able to predict kind of two modes, like to make two types of prediction. One is the general, more like behavior cloning, and the second one is conditioned by high advantage input. And to do it, we need to add extra input. Yeah, so here I simply add one more vector, one more token input to the VLM part. I call it advantage here, but it's actually kind of advantage indicator that is trained embedding that I send to the policy only when I need to predict good actions. When I need to predict like any average actions, I simply don't send this vector as input at all. Then, and this is like pretty big addition, I have multiple auxiliary predictions that are predicted directly from the model itself. So as I said, I combine kind of value function prediction with the actual policy into one model. So I don't have any specific value function. On top of it, I add some extra predictions that are also used in the final prediction logic. There are three new kind of input vectors, and I use like transformer output of these vectors to make these auxiliary predictions. Let's talk about them one by one, starting from the current query. So current query is the vector that is kind of inserted into VLM right after images, so it can see only images and nothing else. And it makes a lot of predictions related to the current state of the environment and the current state of the garment. First of all, it's predicting garment type. I'll discuss a little bit later how I use it. Then it predicts success probability. This is very important part of my value function. Basically, just given an images, what is the probability that we'll successfully complete this task? Then it predicts completion. Again, given the images and given that we'll actually complete this task in the end, what is the current completion %? And then the last one, sorry for jumping, the last one is time to completion, is some kind of combination of success probability and completion. And this is what the physical intelligence in PyO6 uses as a value function, or at least something very close to what they use, with again some corrections. I tried to use it and I had some experiments, but actually I didn't have enough time. So now it's more like a legacy prediction for me. And I also tried some other things like checkpoint success, probability predictions, and so on. So in my code, you will see some kind of legacy things that I tried to predict, and I didn't remove them completely, but I didn't really use them in the like follow-up logic of the policy. And now the key point distances is actually very interesting. So this is something that I would call a cheap replacement of word model in this case. So originally I wanted to add some word model head to my policy. The word model is a kind of model that, given the current state and action, predicts what will be the future state of the system after you apply these actions. There are different approaches to these word models. Sometimes people predict like pixel level word models. Sometimes they deal with some latent space. But in both cases, you will need quite a big models to either like do the pixel level predictions or to transform everything to the latent space and so on. So you need to like run all these computations during the training. And I saw that it will be a lot of waste of resources. And instead, I wanted to do something very, very cheap that directionally does the same. And I realized that predicting key point distances is something that can work. So again, remember that the success of completion of the task defined by positions of different key points of the garment. And these kind of distances between these key points that I use to compute the success are very important parts of the state itself. So if you want to predict the future or current state, we don't really care too much about a lot of things that we can see on the images, but we care a lot about these distances between different key points. So I simply added all these distances as targets for my model. And in this case, in the case of the current query, I just predict the kind of current key point distances just to train the model to kind of understand what I mean by these key point distances. But in like two other inputs, I predict like future position of these key points that we will see after applying all our actions. And this is kind of exactly what word model does. just instead of the whole state of the system, I predict this like subset that is described by key point distances. But I think it's like very, very good and cheap substitute of the word model. Okay, now let's look at these two other vectors like fast query and flow matching query. So these vectors are kind of attached in the end of the fast action prediction or in the end of the flow matching head, and they can see everything, like all the inputs and the corresponding action predictions. And I use these these input tokens to make predictions of basically the same things as the current query does, but in the future. So first of all, I predict the success delta. It's kind of, I don't know, something between like Q and advantage prediction directly. So I predict what is the change in the success probability if we add all the actions and so on as inputs on top of what we predicted already based on only images. So again, if images predict something like value function, then this one predicts not even Q, but more like advantage directly, something very, very similar. If you're applying some actions that are increasing success probability, these are good actions. If you kind of want to execute some actions that reduce success probability, these are bad actions. Then I predict completion just directly, the future completion that we will get after this step. And finally, I already mentioned these key point distances. Again, after we apply the whole predicted action chunk, what will be the distances between all the main key points that we see. Now let's talk about the garment type. Yeah, so I mentioned that I make this garment type prediction. And the reason is because we don't really get garment type as an input when we execute the model, when we evaluate our submissions. So I implemented something very similar to this like simple system 2 from our behavioral solution in the past. So I make the prediction of the garment type during the first few frames, first few predictions of every episode, and then simply use this prediction as an input for the rest of the episode and kind of feed it back inside the model. So you can see that it works a little bit like a system 2 in the very beginning of the task. It decides what exactly it should fold and then gives this input to the model. In practice, I'm not sure if it's important because these predictions are very, very good, even when you apply prediction in the middle or in the end of the rollout of the episode. It works very well, so there's 99 point something accuracy and so on. So maybe if I wouldn't do it, there would be absolutely no effect. But again, I somehow started to do it from the beginning and only very late realized that probably it's not so important. So this is kind of a bit of legacy logic that cannot be removed because then policy will not work properly. But yeah, but in some cases when the actual task definition is harder, maybe it makes sense to use this kind of predictions from the policy itself. And then finally, I realized that when I provide just one vector for garment type or one vector for advantage as an input, it's not enough because all other inputs, all other tokens in the VLM part can simply dominate because of their quantity. And your final action predictions, your final flow matching action expert is not conditioned enough by these inputs. On top of these inputs to VLM, I added extra direct input to the flow matching through the AWR RECAP. I will not explain what it is. It's just a way to condition your flow matching or your transformer by predicting some bias of the scale and so on. So this AWR RECAP was already used inside the PyO5 to provide the time conditioning for flow matching. I simply added 2 other factors to it. And I believe that this conditioning became better. But again, this is one of the things that I didn't properly ablate. And finally, let's quickly look at the attention mask. Yeah, so the attention is not strictly after regressive, not strictly bidirectional. It has a few blocks. The first block is the images and the current query that I discussed. So current query cannot see anything else. It can see only images as an input. The next block is state and garment type. So garment type obviously should follow current query. Otherwise, current query will simply look at it for the predictions. But state is in this block just because it's a bit less reliable, it's usually more noisy, and I don't want any of the current query predictions to overfit to the state, so this is why I put it in the separate block. And then advantage is the last one. Nothing can look at the advantage during the prediction. And then finally, the fast and the flow matching predictions, action predictions, they can see everything before them, but they cannot look at each other. So this like two completely independent like branches that predicts actions separately. That's it. This is how attention works in this case. This is my final policy architecture that I used in this competition. If you want more details, please refer to my tech report and the actual code. You can see the actual implementation, how all of it is done. Now let's talk about the rollout collection. This is the second big part of all the reinforcement learning cycle. So the idea, again, of the whole approach is that we train the model, train this policy, it's getting better and better, then we collect more data, more rollouts, and then use these rollouts to make policy even better. So remember, our policy works in such a way that whenever it's trained on some data set, it eventually becomes slightly better than the policy that collected this data set. So if you just keep repeating it, keep running it again and again and again, it starts to improve more and more and more, and eventually like evolves in a very, very nice, robust, and stable policy. And this is exactly what I've done. There are a lot of technical optimization that I did because this data collection is kind of bottleneck. It takes around maybe like 30 seconds to collect one episode on average, so it takes significant time. I tried to make this simulation collection as fast as possible, as optimized as possible. So I played a lot with like resolutions and cameras. I tried to adjust some parameters of the overall environment and simulation to make it a bit faster. I played with the again some format that I used to save videos, because even like video saving actually takes some time after the rollout is finished. I implemented like multiple workers that are working in parallel and running multiple simulations simultaneously. I also implemented some things like episode kind of cut out when I see that policy already stuck and doing nothing, but there are still 10 seconds left. I don't wait for this 10 seconds. I just stop episode there, and so on and so forth. So I did like a lot of these small optimizations, and I encourage you to look into the code to actually learn about them. But today I want to talk more about more high-level strategical decisions that I made. And two main things there are augmentations or domain randomization. I think it's like more popular term in robotics, but it's very, very similar to augmentation word. And the second one is the rollout collection strategies. Let's start from the augmentations. Image augmentations is a very, very old and classic technique in computer vision. And in all the computer vision tasks, it's used all the time, everywhere. So it's like very, very default thing. I even found this article that I wrote, I think 7 years ago. And you can actually read it because most of the information here is still very relevant. And I believe that it's very, very underutilized in robotics. So whenever I read different papers or I see different implementations of some models, people don't use image augmentations. While it's in practice, it's like very good tool. And I believe that it's like very, very, very applicable in robotics, because we want our models to be very, very robust to different changes. And what image augmentation is doing, it's introduces different distortions or different transformations to the images. And while we apply these transformations, the actual information in the image stay the same. And the model should learn the kind of actual important things on the images rather than some artifacts. So again, I will just refer you to this article that I wrote many years ago. It explains a lot of approaches and a lot of kind of nice things, and even give you some tool to experiment with these augmentations. In this case, I just want to say that I did use some augmentations during the training process. So I apply some image transformations whenever I train my policy. But also in the robotic specific case, we can generate a lot of augmentations. Again, it's often called domain randomization during the actual rollout collection. So we have like two places where apply them. So one, image augmentations can be applied during training. And again, we can introduce a lot of different things that will make our policy more robust in the end. And the second is something that we apply during the rollout collection. Yeah, and now let's see how we can apply different domain randomization using parameters of the actual environment, and how can we collect already kind of randomized and augmented data in the first place. Let's look at the typical rollout. Everything that you see here is simulated. So we simulate the robot, we simulate the garments, all other objects, table, lights, all the physical interactions, all the physical properties, all the colors. So everything, absolutely everything is simulated here. And it means that we can control it. So we can change any single parameter that is used to generate these things, and we will get slightly different image. So let's look one by one what we can achieve. A quick warning, there will be a lot of flashing colors in the next 2 minutes. First of all, we can simply replace the pattern of the garment so it looks different, and it can generalize better to different garments. Alternatively, we can override some colors of the garment, and again, it helps generalization. And the nice thing that we can change colors even constantly every single frame, and we will still get valid rollouts because our policy is memoryless and it doesn't remember the color in the previous frames. This example is a bit harder to see, but I'm changing the lighting a little bit, and you can see that intensity of the light is changing every frame. We can also move the camera position a little bit, and you can see that here the top camera is slightly rotated and we look at the same image from different angle. All the previous rollouts replayed the same successful episode, but here is an example where you cannot do it because I moved arms a little bit and you can see that the position is slightly different than usual. And here it's not visible at all, but I changed some physical properties of the garment that can be useful for generalization. In practice, I combined all these randomizations and also others that I didn't even mention here, and apply them randomly with some probabilities during every rollout. So this is how my rollouts look like. Make sure that your randomization, your augmentations aligned with the environment in which you're going to deploy your model. If you want to run it in the same environment where you are training your model, then you don't need to go very, very aggressive. And of course, you should never break the actual physics. And here you can see how the rollouts look for the real round. So the camera position is different, the camera resolution is different, the robots are orange, and so on. So when I prepared simulation data for the sim to real transfer, I applied much more aggressive augmentations comparing to what I applied for the first round of the competition. And now let's talk about the rollout collection strategies. So what I mean by this? In our case, we were trying to solve multiple problems simultaneously. Yeah, technically, you can say that every garment type is a separate type of problem. And also inside every garment type, there are different garments with a little bit different visual features and physical parameters and so on. So basically, all of them are a little bit separate tasks. And then you need to decide which tasks you actually collect data from. So the most straightforward approach is to either just run all of them, collect one episode with each type, or maybe sample them randomly. And of course, this is the most straightforward way. It's the most unbiased, and I definitely used it. So it was one of the most kind of popular strategies that I used. But then there were other approaches. Imagine that you have different garments, and for some garments you already have success rate close to 100%. Collecting more data with these garments doesn't actually improve your policy too much, because policy is already solving it very, very well. On the other hand, you have garments that are very hard, and you have success rate close to 0. And collecting this type of data also not very important, because you will not get any successful rollouts, and there will be nothing to train on. So eventually, these two things are not so good for your policy to improve, to train. But what is really good is to collect something that has, let's say, 50% success probability, because sometimes it fails, sometimes it's not. You get quite a lot of space like for improvement, and at the same time you collect episodes that are successful, and that can be used as a positive signal to your policy to train. So I implemented this approach, and I used the configurable target. So it wasn't always like 50%. Sometimes I just looked at it and it looked like I need to focus a bit more on like harder cases, and then I set it like to 40%. But the main idea is that we sample the garment that we collect in episode 4, depending on this garment current success rate. The garments that have success rate closest to our target success rate are the most useful for our training, and we try to collect them most. Other garments are kind of maybe not so useful, and we still sample them from time to time, but not as often. So this is the curriculum approach, and I used it all the time. It was very useful. Another approach to collecting data is simply the success replay. So remember, we have a lot of augmentations, yes? And when we run one episode, we simply kind of collect data only for like this one set of parameters that we randomly selected for this augmentation. But if it's already a successful episode, what we can do, we can restart another episode exactly from the same state, and then without using any policy at all, simply replay all the actions. And if we are lucky enough, so if the kind of randomness or stochasticity of environment doesn't hurt us too much in this case, we'll also complete this task successfully. And the thing is that we can apply very, very aggressive augmentations in this case. So for example, we can move cameras completely to different places. We can change all the colors. We can change all the lighting and everything. So unless we are not touching physical properties, like we are not moving the robot, we are not like rotating the garment where exactly we put it, it will still be success. And we will get kind of very nice, hard augmentation rollout that is also very useful for us during the training. And especially I used this in the second part of the competition when I needed to move from simulation to real life, real robot. I realized that there are like a lot of inconsistencies, for example, in camera position, in simulation, and in the real setup and so on. And I kind of aligned simulation with the real robot, and then ran a lot of successful rollouts and like just replay them and collect the data that is much more similar to the setup that we needed to deal with in the final round. So yeah, this is a success replay approach. On top of it, I used what I called semi-success replay. It's a bit more like delicate approach. So here, whenever I run the rollouts, whenever I collect new episode, I try to detect whether we get like some success, intermediary success, whether we, for example, reach some checkpoints in the middle. And then if I kind of reach checkpoints, if let's say I solve half of the task, but then for some reason the success probability drops a lot and I fail the task, it means that probably I was doing something right and then just made some mistakes in the end. And what I do, I collect these rollouts, then I replay them the same as this success replay, but without very aggressive augmentations, until the point where the success probability actually dropped or a little bit before it. And then I collect the rest of the data with the policy. And in this case, we can kind of collect extra rollouts that are eventually successful because we managed to really solve them. In this case, because again, we were like some very, very close, but then model made some mistake. And it's also pretty good training data because in this case, we have one rollout where we tried and we kind of failed starting from this state, and then another rollout where we tried and we actually succeeded starting from the same state. And this is the very, very important data for the reinforcement learning training. And finally, there is what I call hard mining, is kind of a little bit opposite. This is the case where I tried to generate very hard initial states or very hard states in the middle of the task rollout. And then after a few iterations of training, when policy became like better and better, I tried to replay it and try kind of resolve it eventually. I, in the end, didn't use it so often because when you run this hard mining, you have very low success probability because all these cases are really hard. And even so, every success is very valuable in this case because it's success on the hard case. You need to spend much more time to generate this one success. And then eventually, again, I didn't ablate it very well, so I'm not sure if it's good or bad decision. But I think that running something like curriculum is still better, and eventually it's better in this trade-off of how much time you spend versus how valuable each successful rollout is. And yeah, so I use this hard mining somewhere in the middle of the training process, but by the end I switched mostly to the other approaches and other strategies. In the end, I collected thousands of these rollouts. I had a lot of them. I applied some weight decay for old rollouts. So I tried to push weight as much as possible to the most recent rollouts because my system allowed to collect a lot of them and it was enough for training. And kind of the old rollouts were more like extra regularization, preventing of forgetting and some other things. So I believe that this new rollouts collection is very, very important. So my approach, even though it's offline policy training, I think it works much, much better when you do it in this more offline plus of policy manner. So yeah, I recommend, even if you use offline reinforcement learning, try to collect more and more and more rollouts and use a lot of recent rollouts in your training mix and try to apply some lower weights for all the old rollouts. Also, in the next video, we'll discuss why it's important to actually, in my setup, to reduce weight of the old rollouts. Otherwise, they polluting data with these stale value predictions. But again, this is a topic for the next video. And for now, I just hope that I managed to explain the main ideas behind the data collection that I used. Thank you for watching. I hope you enjoyed this video and learned a lot of new things. If so, please like and subscribe. Also, if you have any comments, please ask them under this video. And also, as this is the part of the 3-video series, I will try to have some Q&A or at least incorporate the answers to the main questions into the following videos and kind of go deep into it. So if you have any questions about this particular video, or maybe you read my paper or try to run my code and you have some extra questions, or you have some questions in general that can touch some topics that I'm going to discuss in the next videos, please let me know about it and I will try to include it into the agenda next time. And that's it for today. Thank you for watching and bye.